Okay, so now I'd like to introduce some audio analysis techniques to you all. Back in 1768, back in sometime between 1768 and 1830 when he was alive, Jean-Baptiste Fourier made this mathematical discovery that any periodic sound can represent it being using only sine tones. And last week I did very briefly talk about additive synthesis. Let's tidy up this. And we started to look at how we could take a number of different oscillators and add them together to produce more complex sounds. So in this PD patch we had a basic oscillator here, which we set to be to output the pitch of middle C. Hopefully you can hear that now. And by adding in additional oscillators, you could start to get more rich and complex sounds. Turn off audio for a sec. So what Fourier found was that basically given enough oscillators, if you add them together, if you add enough oscillators together at different sort of amplitudes and different frequencies, you can represent any sound. And I've actually one of the I think it was Oscar in one of my tutes found this video which shows how you can add a number of sine wave oscillators together to produce something beginning to approach a sawtooth wave. So let's quickly play that. It's only a 30-second video. Hopefully you'll be able to hear it if I boost the volume a bit. So hopefully, as you can see and hear there, the person who made the video is adding more and more sine waves into the signal, and as they add the appropriate number of them, and as they add more of them with the appropriate frequencies, the shape of the signal starts to get closer and closer to a sawtooth wave. So it's one example of showing you how a number of sine waves can be combined together to produce more complex sounds. And now, using something called, where's my slide? Yeah, using something called the Fourier Transform, you can actually take some audio and analyze it and unpack and identify the component sine tones that make up that sound, or the component sine tones that, if you combine them together, would be a close approximation of that original sound. There's a really, I won't play it now because it's a few minutes long, but there's an excellent video explaining this in very straightforward terms that I highly recommend you check out here. So the link's in the slides that'll be on UTS Online, so do have a look at that. But the kind of thing we're looking at is the kind of thing the Fourier Transform allows us to do is, let's open up this video. The Fourier Transform lets us take some audio signal, like this music that's playing here, and we can analyze it, and we can find out what's the strength of all the different component frequencies that make up that complex sound. So we're seeing like a bar graph here, which is showing us, oh no, this person wants to show us how clever they are at electronics. I just wanted to use their graphical equalizer type display. It's showing us what the power of the different components of this complicated audio are at various moments in time. So in PD, there is a number of objects that help us do this. There is a real-time fast Fourier Transform object, RFFT, provided, which when we feed an oscillator into that, will essentially spit out a series of numbers that show the power of the oh my goodness, I'm confusing myself. It shows us the power of the different frequency components that make up that sound. So if I send in an oscillator of 440 Hertz and bang the object, we can start to see each one of these numbers represents sort of the amplitude of a particular band of frequencies. And we can see as we go up higher and higher, there's less and less power there. Most of the power is concentrated down lower here, where we're in the around about the 440 Hertz zone. But I can show you a more, hopefully more more easy to understand example than that. That was this one. So this one is showing us a little bit like that sort of spectrum analyzer we were seeing before on the YouTube video. As I speak into the microphone, I'm feeding the analog digital converter into that RFFT object and essentially writing the output of that into a little display here, a bar graph type display that's showing the component frequencies of my voice as I'm talking. So if I make more of a white noisy kind of sound, shh, you'll see a more even distribution of powers in the various frequency bins there. And at the moment, with my voice, most of the power is concentrated down in these frequency bands down here. There was another example too. Yeah, similar example to what I've already shown, just graphed in a slightly different way. Again, taking an oscillator output, I can change the frequency of this oscillator, and as I move the frequency of the oscillator up, you see that the FFT is identifying that all the power in that signal is moving up and down the frequency band. So essentially what I'm trying to explain here, and possibly not succeeding very well, is that we're taking our digital audio signal, which is an audio signal over time, in other words, where our x-axis is time and our y-axis is the movement of a microphone membrane or a movement of a speaker in terms of digital audio. And we're moving from that view of an audio signal over time to a snapshot of the frequency components at a particular moment in time. So this bar graph here is showing us, okay, at this given moment in time, this is the different frequency components that are present in that signal, and this is their amplitude, this is the power of them. So we're moving from the audio signal over time to a snapshot of frequency components at a moment in time. In other words, we say that we're moving from the time domain to the frequency domain. It's what digital audio people say. And we can also move back again. So if we have a series of snapshots showing the power of the various frequency components in an audio signal at moments in time, if we have a whole series of those at different moments in time, we can move from those back to the time domain if we want to. And this can get pretty complicated, as my verbal stumbling is probably indicating. But a useful application, if we're thinking about sort of being interactive media designers and users of this technology, perhaps we don't have to understand too much of a low level, but we can understand what the implications are and what you can use it for. So a useful application in this case is to manipulate a sound using a kind of graphic synthesizer, kind of graphic equalizer interface. It's not a graphic equalizer. What do you call those things again? I'm having a mental blank. It'll come to me later. One of those interfaces with lots of little knobs arranged in a line, and you can adjust them, and each one adjusts the power of a particular frequency band. Oh goodness me! I can't believe I forget. Anyway, not important because I'm about to demonstrate it. I've got a little patch here, which is let's bring this all up. Hopefully you can hear there our old friend, the sample from Blood, Sweat and Tears that we looked at in the previous video. We've got that playing, and we're feeding it through a Fourier analysis, so we're breaking it down into its frequency components, and then we're feeding those through this graph here, which it is a graphic equalizer. That is the term I'm looking for. I was right the first time. We're feeding them through this sort of graphic equalizer type interface, which hopefully, as you can hear, if I bring down these values here, the high frequencies start to be reduced, quite drastically reduced. If I bring down everything, we can hear almost nothing. I can barely just hear some little audio sneaking through there, through my speakers, but I doubt you'll be able to pick it up. So using this kind of interface, I can sort of zoom in on particular parts of the audio spectrum and say, yeah, I only want to hear the frequencies in the middle. Let's keep those up and bring everything else down. So like a souped up tone control, in other words. So we're moving from doing a Fourier analysis, breaking down our signal into all the component frequencies. We're then doing some maths on each of those component frequencies and sort of multiplying them by the values I set in this interface here, and then doing an inverse Fourier transform to transform it back into an audio signal that we can then output to our digital to analog converters. So hopefully that gives you a sense of, let me just turn that audio off again. Hopefully that gives you a sense of the kinds of things you can do using this underlying Fourier transform, inverse Fourier transform techniques. Again, at the level of this subject, I don't expect that you would be able to write your own Fourier analysis or inverse Fourier transforms or anything like this, but you should know that they exist, and you should know that they're in PD, and you should have some ideas about the kinds of things you can use them for analyzing a signal, for identifying the component frequencies that make up a signal, and potentially for manipulating those component frequencies and then sending them back out again as a changed audio signal. Okay. And before I move on, I also wanted to briefly talk about a very useful object in pure data, particularly if you're doing kind of musical interfaces or gamifying some kind of singing game or something like this. if you're making things along those lines, you'll find the Fiddle Object super useful. So the Fiddle Object lets you analyze an audio signal in terms that people, particularly people who have had some kind of basic musical training, would more intuitively understand. So if you want to, for example, identify what pitch someone is singing, or what what note they're playing on a guitar or a trumpet or something like that, you can use the Fiddle Object to do that. And Fiddle will also be able to analyze and tell you what the volume is of the audio that's coming in, and a bunch of other things as well. So let me open up Fiddle and show you what it can do. So here we have the Fiddle Object, and you can look in the documentation to see what the arguments are. This is pretty I think this might actually be the default arguments, but I'd have to check. But let's first of all, before we get into anything or any of those sort of details, let's look at what you can get out of Fiddle. So when I have the audio turned on, a lot of stuff starts to happen. Let's look at the different outlets we can get. Out of this outlet, we can see what the MIDI pitch is of a note that I might be playing on an instrument or singing. So if I go as I move up the chromatic scale, you can see that note incrementing as well. Fiddle can also, at its second outlet, tell us when it's detecting an attack. In other words, when it's detecting, or when it thinks it's detecting a new note being articulated. That could be if there's transitioning from silence to some audio event, or when the pitch of a note is changing, it will tell you that it's detected an attack. But so when I make noise like this, but you should see that each time I sort of create a new note from silence, it's indicating it's detecting an attack. We also, in real time, excuse me, get the MIDI pitch coming out of this third outlet. And if I do a bit of maths on that, I can figure out what note is coming out of it, whether it's a C, D, C, C sharp, D, D sharp, etc., etc. I can get out of Fiddle. I can also get the frequency in hertz out of that by using the M to F object. I think we looked at its twin object F to M last week. We can get the incoming volume in decibels of the output, and we can, if we want to, visualize that. And quite interestingly, we can also get the pitch and amplitude of the frequency of the component frequencies that make up this sound. So that can be quite a useful thing if you want to take a sound and resynthesize it in some way, which can be quite a fun thing to do. And I'll give you an example of that. Actually, I'll give you an example of that now. So because of that the sort of principle that Fourier discovered, we know that we can take a sound and resynthesize it using only sine waves. Let's do a very quick and dirty example of that to show you how that works. So if we take again our sample of Blood, Sweat and Tears, Go Down Gambling, the same sample we've been using in all the other examples. If we take that and read that file and send the output into Fiddle, Fiddle will analyze it in real time and tell us, what's the frequency of the, it'll make its best guess about what the frequency of the notes are that are coming out of it. It'll tell us the volume. And if we look at its last outlet, it will tell us the frequency components that make up the sound. So if we take those frequency components and feed them into oscillators, we should be able to resynthesize Go Down Gambling, the Blood, Sweat and Tears song. We should be able to resynthesize that using only sine wave oscillators. So let's have a crack at it. Let's see what it sounds like. I'll just bring the volume up a bit. Turn the audio on and let's load in, go down gambling. Let's have another listen. Okay, so once again, let's hear our original sound. Oops. Let's very quickly just patch in. So that's our original recording. And here's our re-synthesized version using only 3 sine waves. Okay, so it's not going to win any awards, but I think you'll agree that for using just 3 oscillators, that's actually surprisingly good resynthesis of that digital recording. And Fiddle can output more, I think any arbitrary number of these sort of pitch and amplitude pairs for at its third inlet. So we could keep adding oscillators to get higher fidelity synthesis if we wanted to, simply by doing something like this. I think I need to tell Fiddle to output 4. So we can simply add more oscillators like so. I don't know, adding 1 will help. But it might be a fun exercise for you to try in the labs to add a bunch more oscillators and see how close you can get to the original. So that's all I wanted to cover for the analysis side of things this week. Introduce some very basic concepts of Fourier analysis and what the implications of that sort of thing can be, and how you might apply them. Next up, I'm going to briefly talk about some filters, and that'll be it.